All right, welcome back to the Nexus Podcast. Deral Heiland is my guest. Deral is the principal security researcher for IoT for Rapid7, and he's been part of some great research on exploitable weaknesses in cellular-enabled IoT. So that's what we're going to talk about. How are you?
Yeah, I'm doing good. Yourself?
I'm doing good.
All right.
Doing good.
All right, great.
Glad we can do these face-to-face. I do a lot of these remotely, so
it's always better.
These are a lot better. So good to meet you. Tell me a little bit about your day-to-day, your background.
So as a principal security researcher on IoT, obviously the focus is in embedded technology, right. IoT technology, and it's around discovering security issues, vulnerabilities, failures within the ability to deploy these technologies.
Yep.
Trying to always come up with methodologies for us to start thinking about risk in those environments, because if we don't know about the risk or potential risk, we can't really mitigate them. So the goal is to discover those type of things. Sometimes it's deep dive into hardware like this research was.
Sure.
Others, it may be high level on how you deploy and maintain and manage those technologies and decommission them and things like that. But the ultimate goal is, how do we deliver better security? Mm-hmm. And that's where the research always meant to go. Or we also focus a lot of the research around testing methodologies.
Yeah.
So pen testers that do IoT technology testing will have methodologies, and the ability to look deeper and further into the products.
Right. So this feels really niche, though, and I know this is kind of like part 3 of this overall research project. Is that fair to say?
Yes, it is.
Yeah.
Yes, it is.
So what was the initial motivation to look at this?
Okay.
Are you seeing a trend out there? Or?
Start looking at cellular-based IoT, we were seeing this trend. We start seeing more and more devices have cellular for back-end communications out to the internet or to back-end networks.
Sure.
Devices, everything from medical wearable devices, cars, transportation, they all have telemetry units as cellular, and they call home. We also, I was out to CES this year, and you see this massive increase in autonomous robotic systems that have to communicate out, and they often have cellular technology. And also our pen testers were starting to engage more tech that had cellular in it. And the goal was to get past that, hey, there's a cell module, but I can't see the communications, it's encrypted, it's FCC regulated. How do I know what's flowing through that line? And that's where we got into the idea of inter-chip comms.
Okay.
Let's start looking at that communications between the main CPUs or MCUs that exist on IoT technology and the actual cellular module, and start analyzing that. And then that led to, hey, can we send data into that? Can we control the cellular module? What can we make it do? How's it work in detail?
Yeah.
And how to leverage that in our testing, or how someone would leverage it in attacks.
Mm-hmm. So before we talk specifically about the research, in a factory setting, for example, what would cellular-based IoT be handling? Or
I think in a lot of cases, a lot of these places have remote sensors. Like you have gas pipelines or things like that. You may have a lot of sensors that collect telemetry data and send it back over the cellular to things. But often it's the remote devices that don't have the ability to have an Ethernet connection or standard Wi-Fi connection because of the distance. Is probably the key thing. Any environment would have that. You might see cellular being implemented.
Right. And so they're interacting, obviously, with the cloud or some kind of IT service before, in order to ship that data through.
So in some cases, these devices, they could actually use like private 5G or something. That's something we've seen advance up. So you may have sensors have that ability to go straight back into your corporate network. You may have ones that go out through very direct private APNs that go VPN into a network.
Okay.
And then you have some that connect right out to the internet. They may connect to the standard S3 buckets. They may do MQTT controls out to the cloud services and things that are actually on the internet. Mm-hmm. So you have a whole gambit, and the risk of those vary from, hey, is it going to the internet? Is it going to a private network?
Right. There's
a big difference between the risk model that could exist there.
Okay, so before we talk about this phase of the research, which involves weaponization of the previous two, kind of walk me through from a high level the first two kind of segments of this research.
So the very early research probably started like 6 years ago.
Okay.
Where we were looking at devices, and an IoT device, and I'm like, I really want to understand the end-to-end security. And if we're doing, for example, not cellular-based, but let's say we have a device that has a bridge, and you connect to it with various RF. It could be Zigbee, Z-Wave, pretty much Bluetooth,
Sure.
low energy, things like that. What if that's all encrypted? It's really hard to see it. It's difficult to really find out what's going on there if it's done right. And if it goes out the other end over Ethernet or Wi-Fi and they're crypting it there, those are good security models. But now as a tester, I don't really have the ability to see that whole security model from end to end. But we found out if I analyze the chip communications on the actual board between microprocessors, the communication modules and the main CPUs, I can glean tons of data on how this device handles all of its security in the background. And that was the first phase. And then it progressively went, as we've seen cellular technology, to that next phase is like, okay, now we have cell devices in here, cell modules in these. How do they work? I had no clue how they work. Didn't know anything about them. So that was a challenge. How do these things function? So we got data sheets, development boards, devices with cellular modules in them, pulled down all their AT command manuals. How do they take commands? How are they programmed? How are they controlled? How do the CPU talk to them? And we built all of that knowledge. Once we figured out how we could talk to them, the next thing was, how do we connect to them? So then we get into the hardware hacking. How do we do it over USB? How do we do it over serial? And then, okay, now that we can connect to them, now we know the command structure, let's start sending them commands. Let's start asking them to carry out functions for us. Let's start telling them, like, hey, start setting up raw sockets, HTTP connections, all of this type of stuff on our behalf so that we can get insight into their whole trust relationship. Who trusts them, and at what level do they trust them? And is there shared trust between different devices? A company produces 10,000 devices and they sell it to 5,000 people. Now all of that is a big ecosystem. Now these devices should not share data. We would expect them not to. But
right.
How do we know they don't? How do we know they don't have a shared trust? We don't know unless we test it. So that's where we got to the point is like, let's build the methodologies so that we can validate those trust associations and see if there is issues. And then start talking about, well, if there are issues and we encounter them, we can now mitigate them because we can understand and we can test for them.
So these are all legitimate functions you're asking it to do and just kind of
we're not
see
injecting any kind of malware or any code or anything like that. We're using the functions of the cellular module to carry out our bidding for us.
Yeah. So this is the realm of advanced attackers if someone chooses to kind of exploit this.
I think it is, but the crazy things is there's complete manuals out there on how to talk to these things. Most of the manufacturers produce their AT command manuals that have all the command structures, all the syntax on how they work. So if anyone wants to do it, it's no different than just learning how anything else works. The data's out
spending
there.
Spending
the time. I think the harder part is, in some cases, more the hardware hacking. How do I tap into that circuit? How do I interact with that circuit? And dealing with the electronic nuances that may be involved in that.
And was that prior to this weaponization phase? You had to kind of sort that out first?
Yeah, we sorted that out first. I think paper 2, we got into all those methodologies. It's like, how do we interact with this circuit? How do we connect to it? How do we find the circuit? How do we figure that out? So we built these methodologies and then went through a whole complex level. Here's the easiest way, but what if that doesn't work? What do we do next? Well, we pull the board off, pull the module off the device, and then wire in our own circuits, put the module back on. Now we have access to those communication lines. It's gone down to the point where it's like, hey, what if I look at this module, I turn it up on edge, and I can see the land grid arrays around the edge of up underneath the chip? Can I use acupuncture needles and actually insert acupuncture needles up under the body of the chip?
You went deep.
So we did that, and that worked. And then it was like, okay, what if all of that fails? And then we start going, okay, once we map out the structure of the board and where the most common locations may be for these circuits, and if they're not on the surface of the board, they're in one of the sub-layers, how do we cut into the board? So we sacrifice the board and we start delayering sections of it until we find these runs. And once we found these runs in a pinpoint place we can penetrate through there, then we can actually take a functioning board, do those penetrations, tap into the communication circuits in the sublayers of the board. So we took it from the most easiest finds all the way to what if all of those fails, all the way to the complex. And we tested every one of those methodologies in the lab to see how viable it was.
Right. So take me into the current research, the weaponization part of this. First of all, are you seeing any types of attacks in the wild that might be kind of leveraging any of this? Or?
Not in this capacity, and not yet. Not yet. It doesn't mean they don't exist.
Sure.
Because obviously you're in the device, you're communicating on its channel using its trust association. May not easy to spot.
Right.
And it's the device just communicating normal.
Right. And I mean, depending on the industry, there's a lot of value to something like this for an attacker.
Yes,
I would assume.
Exactly.
Yeah. Okay, so start with the trust relationships. Kind of explain what you mean there in terms of, like, is it just kind of a native trust between the...
Yeah, I mean, we'll start off with the most simple.
Sure.
So a lot of consumer devices don't go into a private network. They connect out to the cloud. They connect to like S3 buckets. And we can assume we can make assumptions that that's done correctly, but there may be devices that actually share S3 buckets or back-end storage in the cloud.
Okay.
That means the device that I purchase looks like it's functioning normal. It's authenticating out, because the goal with this was let the device do all of the authentication for us and just use it as a tunnel to get in.
It. Okay.
So how are these devices connecting out there? Are we failing at that machine-to-machine comms? That's like, hey, it's just a machine talking to another machine. What risk is there? There's no humans in there. So we inject us humans into that, and then it's like, what can it connect to? Let's say it connects to an S3 bucket. It dumps everything out of that S3 bucket, and I'm looking at a single device, and it connects out to the S3 bucket. It authenticates. It's trusted now. It starts putting stuff out there. Is that S3 bucket shared with any other devices? And you don't know that until you have that insight into it. And then you have the ability. We wrote a basic proof of concept code that would actually enumerate S3 buckets through the device for us and do brute force looking for stuff.
Just looking for stuff.
Yeah, looking for stuff. That's one of the more simple examples. The more complex example is some of the higher end devices, transportation, autonomous robots, maybe medical devices.
Right.
There's even certain industry level tracking devices that are fleet tracking systems that don't always attach to the internet directly. They actually attach to like a private APN, which is basically a VPN connection into an internal network.
Okay.
So if they connect into an internal network, has good security been done? That means this device can only talk to a certain port on a certain device. That's not the case because of that machine-to-machine trust being over-elevated. Now I can pivot through into that internal network. Now I can actually start running port scans on the internal network. We've written SOC 5 proxies that'll communicate from a laptop through serial to these devices and connect out. So then you can run tools like Metasploit and stuff like that against these environments. So it's that whole trust of the trust relation here is this device has access.
Right.
What it has access to may vary. Maybe simple, not a risk, all the way up to extremely high risk. But that device inherently is trusted, either through its authentication mechanism or just by what it is.
Yeah. And is that necessary, or is it just a matter of convenience on the development and
a lot
implementation
of times
side?
It's a matter of convenience. We want to get a product up to market. Let's make this work, and not considering the potential security implications of that shared trust.
So the device is basically the attack vector to
Yes, it is. It's just,
move further
it's
onto
just
the
an entry,
services.
It's an entry point.
Got it. Okay. So what's possible when an attacker achieves this kind of access and
Okay, we'll take the worst case scenario where I mentioned a private APN, where it's connected into an internal network. This device is trusted in, no one's paying attention to it, it's just doing its thing. We've developed tools, because we want all proof of concepts on this, that gives us the ability to, as an example, through the serial port. It turns out that cellular modules, the ones I've looked at, or IoT class and LTM class modules have two channels. They have a USB channel and a serial channel. Those two channels communicate to the actual cellular module and configure it, set it up.
Yeah.
And they also push all the data from the main CPU. The thing is only one of those is used. The other one's wide open, and it's not turned off.
So there's one sitting there for you.
There's one sitting there. So if you can locate that one, then you can connect to it. The device will continue functioning completely normal. No one will know the difference. And now you have a side channel on the device to set up communication.
Mm-hmm.
And as a proof of concept, on the serial, we wrote a bunch of tools. One was we wrote a port scanner that would actually do rudimentary port scanning using the raw sockets on the cellular module. We wrote a SOX 5 proxy. It allows me to, through serial, fire up a SOX 5 proxy and run most of my applications through that, with some limitations.
Sure.
The cellular module can only do so many sockets at a time. On top of that, we have the USB channel. So in our case, what we did was we hacked the USB on the device and spliced in a multiplexer, a USB multiplexer. It would let us go 2-to-1. So the one side would actually be the cell module. The two side, one would be the CPU, one would be our laptop. So once we got that working, the device would come up, the host would connect to the device, so the CPU would connect to the cellular module, carry out all authentication, passwords, codes, everything. Connect to the cellular network, connect to the back-end network, connect to any VPNs. We'd throw the switch. It would give our laptop an IP address, and you were just like you were connected to the network.
Sure.
Fully functioning, every tool worked, and the USB on more of the LTM1 devices or LTM devices has what's known as ECM. It's Ethernet Control Mode. It's an Ethernet port over USB. So your laptop has all the software, at least all the operating system I checked. So when it sees this ECM on this device, it immediately negotiates USB to Ethernet and gives you...
And you're in.
You're in, full access. And that's how we developed out our tools as proof of concepts. And again, this whole tool suite thing is one to prove that this attack vector does exist, but also to give tools to people that are testing these products for companies. Now they have elevated tools to be able to interact in circuit to actually test the device's security and the trust associated.
So in terms of like what an attack would look like, is physical access required?
Yeah, you're going to have one of the devices. You're going to have one of the IoT devices in your possession. But it's one of, millions out there?
Sure.
So how much trust is there across the different products? Or how much trust is given that device by the cloud, by the S3 buckets, by the back-end databases, or the internal networks?
Yeah, there could be some serious scale there.
Yes.
Yeah. And is there any way to trigger this remotely? Or
No, not at this point.
No.
I haven't identified any methods to attack the device. Now, obviously, if you can attack the device and let's say root the CPU on the device, then you would have that level of access too from a remote attack. So if you can attack the device remotely through some other method, whether it's some RF, it has Wi-Fi in there also, because a lot of these devices have everything. They may have Bluetooth, Wi-Fi, and cellular capability. If you happen to have a case like that and you have a vulnerability on the device, physical access may not be needed, because then if you can control the CPU on the device, then obviously you're inside already.
Right. So are these types of attacks detectable?
That was one of the. Obviously, if you're connecting in or you're attacking somebody's S3 bucket, somebody should be monitoring.
There's a trail there.
Are we being attacked? Has something been exploited? If you're connecting to an internal network, then standard network security protocols come into effect. Are you monitoring? Are you segment? Are you doing any kind of behavior analytics? Hey, I have this autonomous vehicle. It connects out, it transfers this type of data. Is it doing port scans? Is it trying to brute force an SSH on a machine?
Yeah.
Those are key indicators that just something's going south.
Right. But in terms of, there aren't CVEs that can be patched here. This is it back to the drawing board kind of thing? And
I think in some cases with the cellular modules, adding mitigations in there. Like I mentioned, there's 2 channels, only one of them's used. Can the other one, typically the approach is you disconnect it in circuit. But if I have the physical device, I can reconnect to that circuit. That's not a problem, some way or some fashion. But the ability to completely shut it off, that means if I'm using USB, completely shut the serial off so it's not on. And it can't be turned on. That's the thing.
Right.
Because if I have communication to the cellular module, even through the USB, I can reprogram and say, turn your serial back on or turn this back on. So you want to be able to stop those. Now, when I talked about the NB-IoT or LTE-M class devices, none of those I looked at had any kind of security in those. Now, I have been poking around, I'm not going to say the brand, but an automobile telemetry unit that has a cellular module on it. And it's an OEM, so there's no AT manuals, very little documentation. But I was able to find enough technical documentation to determine that some of those features were built into it. It had the ability to program, turn on, turn off various serial and functionalities. But then the thing you also want to be able to, like, let's say password protect those functions. Once the vendor deploys something gets ready to deploy something into the wild and sell it, it'd be nice if they could say, hey, it's time to go to market with this. Let's lock this password protected so that somebody who would connect in would have more trouble controlling or manipulating the device.
Those
don't currently exist. Maybe they should.
So I'm curious, have you heard back from manufacturers? Like, what's the interaction been like? Eye-opening?
In this, potentially, I have not.
Okay.
So this is, in our research, our testing, we use a specific module in our demos. This is not an attack or a target on this particular vendor. All of these classes are all the same. So the NB-IoT and LTE-M classes that I looked at from like a half dozen vendors all function exactly the
regardless
same.
of vendor, right? So, something like this, when you find something like this, where does it fall down? Is it the design? Is it implementation? Again, not to pick on anybody in particular.
I think it's all of those.
Yeah.
It's the design. I'll be honest, when it comes to the cellular modules design, they think about, at least from the physical aspect of the device, they think about security. I have interacted with vendors in the past, and I've talked to some about their module, and I've actually, when I do get a module, or find a device that has a cell module, I go buy a couple of those cell modules, I tear them down. I take all the components off of them, get down to the circuit boards. I may try to delayer the circuit boards. I try to map out the whole thing. And I have to be honest, almost all of them I looked at from a physical design perspective, absolutely brilliant. From a security perspective, to be able to break into the device, it's inherently more complex. Doable, still doable, but much more complex. So I think they do a good job with their intentions of the devices and how they're to be used. But I don't think they ever expected the approach I'm taking on these particular devices. And because of this, maybe we need to rethink some of these designs and come out with capabilities within these cellular modules to be able to add more security. So when a company buys these to deploy in their product, they have a more suite of mitigations that they can implement to improve their product security. And I think from an industry, it would be great to see us move in that direction for some of these.
I mean, just listening to how you kind of broke all this stuff down, it's not trivial. I mean, it takes a lot of work. I've never looked at any of this as complex. I've looked at it as like, and I've done this with a lot of research in the past. Vulnerability research is cool when you can, you send a buffer overflow and you attack a device. It's like, ooh, cool, see what happens,
cool. In this case, it's like, hey, and this is something I've done throughout my career. How's this supposed to work? Now, how can I leverage its expected functionality in my favor? And that's all we're doing here. We're taking something, learning how it works, and going, okay, let's make it do what we want, because now we understand how to talk to it, communicate to it, connect to it. And I think that aspect of research adds a level of complexity in protecting, because it isn't like, hey, I can change the code so the buffer overflow is not there. We do a firmware upgrade. In this particular case, a lot of this is how the device physically
Yeah,
functions,
exactly.
and that's often hard to protect from.
So just as a last question, last thought, is there a next stage to this, or is this wrapped for you guys?
So no, there is a next stage. Not sure if I discuss it here.
That's okay.
But there is a next stage you're going to see coming, that because we're talking about communication outgoing from the device. We're interested in examining communication incoming to the device, and how that would play out, and understanding how that could be manipulated or controlled to have adverse effects. Also, we want to cover the full gambit, so in the end we can better secure the product.
Right. All right, we're going to have to keep an eye out for it. Thanks for joining me. I appreciate it.
Thank you very much.